Okay, let's do the chapter 4 test. So we have the table and this is supposed to be exponential. So if it's exponential, the change should be a same amount each time. And so we're going to kind of average that. So from 23 to 14, it's going down by 0.09. So I'm going to have to take, I'll do this on the calculator so you can see what's going on here. So I got to take where I end up at, 1.14 minus where I started, 1.23. That's the change, minus 0.09, divided by where I started at, 1.23, and I get negative 0.0731 or negative 7.31%. 317, I'll carry out 4 digits. Next one I would do 105 minus 114, 1.05 minus 1.14. That's down by 0.09 again, divided by where I started, 1.14, and that is negative 0.07894 or 7.894%. And then the next one goes 0.97 minus 1.05. Because that one went down by 0.08 divided by where I started, 1.05, and that's a drop of 0.07619, and the last one, 0.9 minus 0.97, which is going to be 0.07, divided by what I started with, 0.97, and that's a drop of 0.07216. So the average, and I want it in percent, so I'm going to take and add those up, 0.07317 plus you notice I'm not putting in the negatives. The answer is going to be negative. I know that, so I don't have to type those in. 0.07894 plus 0.07619 plus 0.07216. And I get 0.03 divided by 1234, and I get a percentage decrease of 7.5115%. That means my exponential model would be starting amount 1.23 times 1 minus this in decimal. So I got to take 1 minus my answer, and whoop, I didn't do that right. 1 minus my answer, and so I got 0.924885 to the t, and that's the amount there will be after t years. Time is in years. Starting amount came from here, and 1 minus I got to subtract this. It's 1 plus this in decimal form. So 1 plus the average of that was what I put in there. Now I can write this in base E, the amount after some time is the starting amount, 1.23, e to the percentage in decimal, so negative 0.07515 t. Or I could take the ln of this and use that. That should be close to the same thing, 0.924855. And it's a little different, but this model is compounded continuously, and this would get us to the same end result as this does. All right, so what's the half-life? Well, it depends on which model you use, but in either case, it's going to be, this would have to equal 0.5. Or 0.5 would have to equal e to the negative 0.075115 t. Either case, I got to solve for the t. This one, I could write it in base 10 or base e. I could say ln of 0.5. E to that is equal to e to this, so I can write this is equal to ln of 0.924855 to the t, but the t can come down. That's from writing this as e to the ln 0.5 and e to the ln of this long decimal to the t. And since they're both e, this would be ln 0.5 equals ln of this times t. And so then I would take ln 0.5 divided by ln 0.924855, and I get t to be 8.87 years. If I do this one, I can write this as e to the ln 0.5. So I got ln 0.5 equals this. So I have to take ln 0.5 divided by that. ln 0.5 divided by that negative 0.075115. And I get 9.22 years. 2, 3. They're near the same. The models are slightly different, but that's kind of the idea behind them. That's all I wanted you to get. Solve for x in the following. Well, these are all powers of 3, so 3 to the 2x equals 3 to the third, 27. Times 3 squared to the 4x minus 3. When you got a power to power, you multiply, so I got to take 2 times all of that. And when you multiply, you add the powers. So I'm going to get 3 to the 2x equals 3 to the 8x minus 6 plus 3 is minus 3. So 2x equals 8x minus 3. Subtract 8x from both sides. Minus 6x equals minus 3. Divide by minus 6. And x equals 1/2. B. Now I can't write them as a common base, so I can go to base E or base 10. If I go 10, this would be log 6. That's another name for 6 to the x minus 3 equals 10 to the log 14 14, that's another name for 14, to the x times 10 log 8. And I could have done ELN 6, ELN 14, and ELN 8, but I did it in base 10. Now here, where a lot of people got messed up, you got to take the log 6 times both of those. You got to distribute this. When you got something to a power, you multiply the powers. So you get log 6 times x minus 3 log 6. Log 6 times the minus 3. And that would be the power of 10. And over here, we got to multiply those. So that's x log 14. And when you multiply, you add the powers. So plus log 8. And at this point, you could go to decimal, or you could just do the algebra. Like I could subtract x log 14 from both sides. Now we get this, all the x's over here, and I could add 3 log 6 to both sides. And so then I would have x times log 6 minus log 14 equals log 8 plus 3 log 6. So I just divide by this on both sides, and I would get what x is. So typing that in my calculator, I could get log 8, close parenthesis, plus 3 log 6. That's this side, and I got to divide it by that. So that answer divided by, and I got to put parentheses around this, log 6. Oh, I didn't hit parenthesis there. Close parenthesis, minus log 14. And I get that x should be negative 8.798. And I could check it. I could store that into x and then type these in. Let's do that. So I got this button down here that says store. If I store that in x, this calculator now thinks x is that value until it's changed by doing some graphing or something else. So I can say, what is 6 to the x minus 3? And it tells me that. And then I can say, what is 14 to the x times 8? And it gives me exactly the same number. So the two sides are equal if I make x be that. Okay, now we're on to three. Log, this is a power, so they can come down and make it square root of 2 times log base 10, which is understood because I didn't say it, of 10. And to what power did I take 10 to get 10? That's a 1 times the square root of 2 would be an exact answer, square root of 2. The power can come down, and then I got 25 to what power is 5? Well, I have to do the square root to get to 5, and the square root is the 1/2 power. So I have x times 1/2, so my answer is 1/2 x. That's the exact answer. And this one, e to the ln 5 pi, is just another way to write 5 pi. 4. When you're adding logs, you multiply the arguments if they're the same base. So we get the log, just a single log, base 2, of these multiplied. So 3x plus 2 times x. Now, I'm going to multiply these together, but I'm also going to change the log base of something, base 2 of something equals 3 to a power equation. It says, to what power do I take 2 to get this? The answer is 3. 2 to the third power makes this. So 2 to the third makes 3x squared plus 2x. 2 to the third is 8. So if I subtract 8 from both sides, I get 0 equals 3x squared plus 2x minus 8. And if that factors, that would make it easy to do. Let's see, 3x and x. And 8 could be a 2 and a 4. So this would be 6 and 4, which would make 2 if it was plus 6 and minus 4. And a minus 4 times plus 2 is negative 8. So that's how it factors. If I set that equal to 0, I get x equal 4 thirds. If I set that equal to 0, I get x equal minus 2. But I can't have log of negative numbers, so this one gets thrown out, and that's the only one that works. 4b. So here we're subtracting 2 logs, so that means it goes to a single log, base 7, of a division problem. 26 minus x over x minus 1 equals 2. Writing this as a power equation, it's 7 squared is this. So 7 squared, 49, is 26 minus x over x minus 1. So I'd multiply both sides by x minus 1. And so I get 49x minus 49 equals 26 minus x. So if I add x to both sides, I get 50x. And if I add 49 to both sides, equals 75. Divide by 50. I get x equals 75 50ths. 25 goes into both. 3 halves, or 1.5. And 1.5 minus 1 is positive, so I can use it there. 26 minus 1.5 is positive, so that one should work. Number 5. So this is the decay model for a radioactive gas, and radon, as I explained in here, is often found in houses, and it's harmful, and so you need to take care. Sometimes you have to do some kind of remediation, some way to eliminate it or isolate it. So we got to figure out the K for radon. So it says 4 grams decays to this. So we start with 4. So A0 is 4.000. So you need to carry several places of accuracy, like 4. It ends up being, after some time, 1.3389. 5 digits, 4 digits of accuracy. So you want to keep the K quite a few. E to the K, the constant for radon, times the time, and this was in 6 days. So if you divide the 4 out, we get e to the 6k is equal to 1.3389 divided by 4 is 0.3347. You need to keep at least that much. Now to get the k, I got to write this in base e, so that would be e to the ln of 0.3347. And then 6k must equal this, so if I have those equal, I could divide the 6 into that, and I would get k. So k is going to be the ln of this divided by 6. So the ln of my answer divided by 6 is negative 0.1824. 0.1824. Negative means decay. So this is a constant, has no units, and I got to use it anytime I talk about radon. So now it says if you started with 20 grams, the amount later will be depend on that. E to this k, negative 1.1824 times the time, and that's 10 days. So I just have to type that into my calculator to get an answer. 20 e to the negative 0.1824 times 10. And if you're doing it on an older calculator, you got to put that power in parentheses. Anyway, we get the amount left. The 20 is going to die down to only 3.22 grams. That's still radioactive. To 3 probably rounded because that's a 7. Half-life. So that's when this part, only this, would be half of the original, gives the new. So we would say 0.5 equals e to the same k, 1824 times t, and we got to solve for the t. But 0.5 is e to the ln 0.5. So this must equal that. So ln 0.5 divided by that constant will give me the time for the half-life. So ln 0.5 divided by negative 0.1824, 3.8 days. Takes 3.8 days for half of it to disappear, another 3.8, and half of what was left will disappear, and it just keeps going on and on like that. And finally, the last problem. If you invest 8,000 at 4.25 compounded quarterly, we're going to use the compounding formula. So the amount after 9 years, so we're figuring the amount. This is not times 9, it's just noting that it's 9 years that we're doing this for. This is the starting amount, 80, that's 8,000, times 1 plus the APR, 4.25, but in the interest rate in decimal. So it's 0.0425 divided by how many times we're compounding in a year? Quarterly. That's 4 times a year, to the 4 times the number of years. And that was 9. So power is 36. So all we have to do is type that into the calculator. Let's see, clear this so you can see it. 8,000 parenthesis 1 plus 0.0425 divided by 4 to the 36 power. And there'd be $11,703.92. 8,000 would have grown to that amount. How long would it take to get to 10,000 if compounded monthly? So we're going to start with the 8,000. 1 plus 0.0425, but this time monthly. So this is going to be 12 times some time to get to 10,000. So to solve this, we're going to divide the 8,000 out. So 10,000 divided by 8,000 is 1.25 equals this number. Let's see what that number is. 1 plus 0.0425 divided by 12. Oop. Something I typed in wrong. I didn't put a starting parenthesis, so go back and just delete that parenthesis. And I need to keep quite a few digits on this. So that's 1.00354117 to the 12t. We've got to solve for t. So we can write this in base 10 or base e. I'll just write an e, so this would be e to the ln 1.25 equals e to the ln of 1.00354117 to the 12t. So this power would come down times this, and it would equal that. So we'd have ln of 1.25 equals 12t times ln of that long number, 1.00354117. So to solve for t, I'd divide by 12 and by that ln. I'll just do that on the calculator. So I need ln of 1.25, close parenthesis, divided by two things, so I got to put it in parentheses, 12 times ln of that last answer, and that would get rid of the 12 and the ln of that, and so I press enter and I get t equals 5.25 years, 5.26 years, for it to go from 8,000 to 10,000. In 5 years and 9 years, it makes it all the way to 11,000. But this is quarterly, this is monthly, this one will grow faster than the other. How long did double if it was compounded daily? Well, this part of the formula would have to be 2 to double the amount to get the new amount. So the 1 plus 0.0425 compounded daily, 365, would be to the 365t, and this would have to be 2. So I would write this in base E or base 10. So e to the ln 2 equals e to the ln of this stuff to the 365t for daily. And since they're both e, ln2 would equal 365t times ln of whatever 1 plus 0.0425 divided by 365 is. So I got to take ln2 and divide it by 365 and ln of that. ln2 divided by more than one thing, 365 ln of 1 plus 0.0425 divided by 365. And I get the time to double is 16.31 years. And how much does it in the account in 9 years if compounded continuously? So that's just the starting amount, which was 8,000, e to the interest rate in decimal, 0.0425, t, and that t is going to be 9 years. So I get to take 9 times that, take e to that power times 8,000, and I get it. So 8,000 e to the 0.0425 times 9. And the amount that would be in the account after 9 years, if compounded continuously, would be $11,727.56, rounding.